Okay, this is it. This is what everything has been leading up to. We have all the pieces to now build a computer. We have our way of representing information, we have our instructions, we have all of our Boolean logic, and our gates, and our adders, and all that. So let's get started. So first of all, it's important to know that there are two components to this. There is the data path. That consists of all components that store or process data. So basically, it's going to be our registers, our ALU, and our memories. So anything that has to do with data. And there's our control. That's going to consist of these components that tell the data path components what to do and when. So that'll include the clock and the control logic. So an example of this will be, for example, all of the selector bits that we had going into our ALU previously when we talked about that. So this is going to be an abstraction for what the data path for R type instructions is going to look like. If you'll recall, we had our 32-bit instruction. It was divided up into some fields. We had our opcode. We had our three registers, RS, RD, and RT. We had a place for shift amount, and we had some function. And what this will basically show you is that we have the 5 bits from the instruction coming into our register file so that it can indicate what register it is that we want to do work with. And this data path is going to constitute of one read register, or 2 read registers, sorry. Those are conventionally RS and RT, and a write register. And the way that this is implemented is, if you'll remember, we saw in previous lectures that you can basically implement this as a big table lookup. So this is really a multiplexer with 5 bits going in, and then telling this register file which of the 32 registers it wants you to do work with based on that. And then once it does that, it'll be able to actually look at the data from the 2 registers. In this case, it would be register 1 and register 2. You would do some useful work on it in the ALU. And this ALU is just going to take those data values in as inputs, do some useful work on them based on what our control input is here. And then it'll come back around as write data. The result of the ALU will is that is. And based on our setting for the register write control bit, if we set it to 1, we will write to the register that we specified as the write register. This is a little bit of a closer view of how each individual read and write port works. So you can see here that they're basically all connected to each of the 32 registers, and then we have 5 bits coming in as input to our multiplexer. And this is just what I said before. It acts as a lookup table where it'll look at the bits that you sent in, determine what value it is from 0 to 31, and from there it'll get the value out of there and send it out as data. So a 32 to 1 multiplexer is really a lot of multiplexers, because you need to start off with 16 multiplexers of 2 inputs each, and that reduces down to 8. All the way down to 1 multiplexer at the very end. So when you do this, you really have 31 multiplexers, and this is just for 1 port. We have 3 ports that look at registers. So that's why we have so few registers, is because there's a lot of overhead to doing this, but it lets us read and write to our registers really quickly. Let's look at our ALU once again. We note that we have our add and subtract module, bidirectional shift module, and Boolean module. Each of these will take in inputs from A and B. A and B correspond to our read data 1 and our read data 2, which are coming out of registers. And then we have our control bits that go into each of the different modules to tell us which operation it is we're going to do. This is a brief review of the MIPS instruction set architecture. It's important for the reasons why I just talked about, because basically each one of these, it gets broken up into pieces, and each of those pieces does something with respect to the entire computer. The instruction ones go into the register file, and they indicate what registers we're going to look at. The shift amount will go into the ALU if we're going to end up shifting. Our opcodes tell us what control bits are going to go in, and our function further specifies those control bits. And you can see that all of this is just information that's going into the CPU. So with just 32 bits, we can do this wide array of operations, which is pretty cool. And we're going to start building from the ground up. First, let's look at how we fetch sequential instructions. So you have this particular module called a PC, and it'll keep track of which instruction we are in memory. So when you have a MIPS program, what happens is all of the instructions you wrote get loaded into instruction memory and get sequentially labeled with an address, and the address that it's labeled with is what the PC counter is for. So we're keeping track of the current instruction that we're on. And so normally we're just going to increment by 4 each time when we go to a new instruction, because you just need to add 4 bytes to get the next instruction in the instruction memory. So that's what this is doing here, is it gets the value out of the PC currently, puts it into an adder that simply adds 4 to this value, and then it loops back around, and you have the old PC value plus 4 coming in and becoming the new PC value. Furthermore, you can see that once you get a value out of the PC, that's going to be the address of the instruction that it is you're going to read. So we send it into the instruction memory box, and it'll then read that instruction and send it out into the rest of the CPU to do some useful work. Alright, so what we just saw is this stuff up here. And so we have all this PC stuff abstracted away. We know that we're going to get the instruction out of instruction memory. And so once we get the instruction out of instruction memory, the computer knows to break it down into its corresponding parts. Its opcode, its registers, and its additional fields. So that'll go in here. So this is all of the registers and stuff we're going to do with them. And then all of your control bits, such as the opcode and the function code at the end for R-type instructions, are going to go into our control logic and dictate what operation it is we're actually going to do. Okay, so now that we have all this information, we can actually do useful work with our ALU, and we've added a couple things here. So note that this is just what I was talking about earlier. Coming out of instruction memory, we'll have our opcode and our function going into the control logic. And then we'll have the register values coming into the register file, each one being 5 bits, of course. And so you have RS and RT. These are your read files. RS is our source. RT is, I guess, our target. And then you have RD for our destination, which is the file that we're going to write to. So the label of the ports that they're coming into are RA1 and RA2 for read address 1 and read address 2. RS and RT are the addresses we're going to read, so that's why. And then we have WA for the write address, and traditionally the destination address is the name of the address that we're going to end up writing to. You have an additional control bit here called WRF. That stands for, I believe, Write Enable Register File or something like that. And what that does is, if this bit is set to 1, it'll allow us to write to the register indicated by the write address here. And then this is just what we were talking about earlier with the flow of data. Once you have your two read addresses, you're going to get them out of the values out of the register. They'll come in through the data into the ALU. ALU will do work with them. You'll get the value coming in as write data, and then if WRF is enabled, it will write to the register specified by WA. So we can see that in order to do this stuff, we have to have our ALU function that actually tells the ALU what it is we want to do, and this is specified by the opcode and the function code in our instruction. And then we have our write enable register file, which tells us if we're going to write or not. And this lets us do the basic ALU instructions: add, subtract, and, or, XOR, and NOR. We can make a simple addition to this that will let us add shift instructions to it. We have the shift amount field in our R-type instructions, which we didn't use for this, but now we can use. So remember, shift amount is just going to be 5 bits specifying how much we want to shift by. 5 bits is all you need because 2 to the 5th gives you 32 possible shift amounts, and you're not going to need to shift more than that since the register only holds that many bits. But you can see that what we have here is coming out of the register data. You can see this is leading into a multiplexer called aselect. And what aselect does is it determines what input A is going to be for the ALU. So you have a choice. It can either be your register data, that's what it's always been before, or you can look at the shift amount, and if you select 1 for aselect, you'll look at the shift amount instead, and this will come in and you'll do a shift operation here. So pretty straightforward, but now you can see that we're going to have to add multiplexers in order to determine, differentiate between which operations we want to do. And with this, you can add all of our shifting operations: shift left logical, shift right arithmetic, to give a few, as well as their V versions. Now let's add an immediate value. So one key thing to note about instructions with immediate values is that we no longer have 3 registers in a shift amount and a function code. We have 2 registers and an immediate. And this requires us to add some multiplexers on the hardware level. So first of all, we'll note that for the register data 2, we've done something similar to what we did before, which is we've added a multiplexer that indicates which value is going to go into the B input of the ALU. And so it's either going to be the data from register 2, so you could have register data 2, or you can have the immediate value. And of course, the immediate value is just gotten out of instruction memory, and it'll come in through the multiplexer. You might need to sign extend if it's a arithmetic operation, and so what we have here is a little module that will sign extend on its way to the multiplexer. To use it, you simply put a 1 into the sign extension bit. So if you need sign extension, that's another control bit you use. You will just simply put it as 1, and it'll pad with the sign if you send a 1 into the sign extension. So it'll just look at the leftmost bit of your immediate and sign extend accordingly. And if it's 0, it'll just pad with zeros. And remember that you pad with the sign for arithmetic instructions, and for logical instructions you pad with zeros. So you have your sign extended immediate value, and it's going to be used here in the multiplexer. And for bselect, if you send a 1 in, it'll look at that immediate value. If you send in a 0 for bselect, it'll simply look at the register data as we've seen before. And note that we have one other place that we have to change because of the immediate, and that is our write address. So previously we were always writing to RD, our destination, but if you look at this instruction, it doesn't have a RD field since it only has 2 registers. In this case, RT is the one that is going to be written to, and what you're basically going to do is you have whatever value you took for bselect up here, and you send it up here. If you have 0 for bselect, that means, well, you're going to do a R-type instruction, and so you're just going to keep RD as your register that you're writing to. But for immediate instructions, you need it to be RT instead, and that's what's going to happen if you have 1 as your bselect input. Note that what you have here and what you have here are going to be the same inputs, so you can't have like a 1 for this bselect and a 0 for this bselect. It would be the same thing. Now let's look at load instructions. This is adding a new module that we haven't seen yet. but we should know about, called data memory. And all data memory is our main memory, essentially. So whenever we are trying to load something out of memory in MIPS, that's where it comes from. And so it's just a continuous block of memory addresses where you can store values. And let's think about what we need to actually get instructions out of there. Well, first of all, we need to get the address that it is we want to look at. And so that's computed and passed through the ALU, and the address we want to look at is sent into data memory. It's then, again, like a lookup table, essentially, where it'll look at the address that you sent into it, it'll get the value out, and that's called register data, or RD. And what we have this new multiplexer down here called WDSEL, or write data select. What write data select does is it tells us which of the outputs we want to actually write to a register. So note that you still have data coming into the ALU here. It's used for the data memory stuff to pass in an address. But now you have that value coming out and you have this value coming out. So you need to specify with a multiplexer which of the values it is you actually want to save in a register. And if you're loading an instruction out of memory, it's going to be the register value that you got out of memory. And additionally, we have a port in data memory called WR. This specifies if we're going to end up writing to register, and in this case we do, because that's the whole point of loading an instruction, is to save that instructions, or save the value of the address you specified into a register. And so that adds load word to our instruction set. Store is very similar. The only difference is now instead you have a value from a register going into data memory. And you don't need to make use of write enable register file because you're not actually writing to any registers here. You're just writing to data memory, which is different. So you have your value going into here. It should still be taking in an address that is going to indicate where we want to store the value, and then it'll do it. I think this ends up not mattering because you're not writing to any registers in the end, so whatever the write data is not going to really have an effect because it's not used in the instruction. Alright, now let's get on to jump instructions. This is going to have us do different stuff with the PC counter than what we've seen before. Previously we're always adding 4 each time, but now we might modify it in different ways. So we've added a multiplexer up here called PC select, and it's basically going to select the program of our PC. And so what we can see here is that when we have a jump instruction, you have some 26-bit immediate, and what happens is the immediate is going to come out of the instruction, so you're placed in instruction memory, and it comes out here into PC select. And so if you select 2 for PC select, it'll get that constant and it'll modify the PC counter to be a function of that. So it'll allow you to jump to that place instead. And that'll do for just regular jump instructions, but note that jump instructions also, we have jump and link. And what jump and link does is it stores the current PC value, or rather the PC value that would have happened next had we just continued going as normal, and it stores that into the RA register. So in addition to doing this work here with the PC, what also happens is you get the value of the PC plus 4, so PC before you did the jump, and that comes in here. And you have it passed to this write data select multiplexer, and that's because you want to write that value to the RA register. So you would have to select 0 for WD cell, and it comes up as write data. And then for your write address, we have renamed what was previously just the same thing as bselect to write address select. So it lets us select between the RD register, the RT register, and register 31, which is RA. So if we're doing a jump and link, you're going to have 2 for our write address select value that's sent into the multiplexer control bit, and that lets us write the address to register 31, which is the RA address, and that lets us return. Okay, now we have branch and equal, branch and not equal instructions. Remember from our ALU lecture that we get a Z flag out of the ALU once we perform some operation, and what that is going to do is it is going to determine whether the values are equal or not. And we're going to do something different if they are equal or if they're not equal, basically. We're going to have a different branch target as a result. And branch target is simply the instruction address that we're going to go to after we've evaluated whether our two inputs, A and B, are equal or not. So what we have here is branch targets coming up here. So first of all, it'll look at PC plus, it'll look at the current PC value, and it'll send it in here, and it'll also look at whatever value it was you sent into the immediate, and it'll come in here, and looks like what happens is it'll then see whether Z is set to 0 or not, and based on that you have your two branch target outcomes, and that'll go into your PC select, and if you select 1 for PC select, and it'll become your new PC value. We now have jump indirect instructions, and what jump indirect instructions allow us to do is they let us go to an address stored in a register. So this isn't anything wild that we haven't seen before, but it's just going to require you to get the value out of the register. And now that we have this, we have a jump target input control bit for our PC selector. So it's going to get some value out of a register and then put that into the multiplexer, select it, and use that to determine the new PC. And then we have all of our comparisons. It's just going to make use of all of the flags we've seen before. So it'll do some useful work with the ALU, then it'll look at the bits coming out of them for our condition codes. And this will add shift set if less than and set if less than unsigned. And we have even more of these. Finally, we have load upper immediate, and what load upper immediate is it will take our immediate value and it will shift it left by 16. So essentially it's an instruction that takes an immediate and is hard-coded to do a shift left by 16. So we've added to our A select a additional option, and if we select 2 here, it'll take 16 in as the shift amount, and that'll come in to here, and our immediate value, it looks like, will come into here as the other input. So you have the immediate value coming in here, it gets sign extend, and it comes through here. So it'll then take value B, which is our immediate value, shift it left by 16 based on our input to A select, which is just 16. And then it'll do all this stuff with write address and everything that we've seen earlier. You're not going to be super responsible for these, but it's important to note that the PC select that we saw now has 3 values that we haven't made use of yet, and it has a couple more that it reserves for reset, interrupts, and exceptions. So on a reset or reboot, we have to set the PC to something different. We have to have interrupts and exceptions for if something goes wrong, or if you have an I/O event, like a system call, for example. You have to stop the program so that it will be able to read in your input, if that's the kind of syscall you did. And you handle it with reserving 2 registers for the operating system, and interrupt handlers. And you can see here that this is where they were used. It requires 2 additional flags to be sent in for control logic, and it requires 1 additional register for our write address select. And it's one of the registers that we've reserved specifically for this purpose. So you can see here, this is our final version of the 32-bit MIPS processor, and it's essentially a synthesis of everything we've talked about in this course. Hopefully you understand this, and if you don't, we'll probably be open for some review sessions or something, but you can also feel free to leave any comments down below, and I'll do my best to answer them. Hopefully these video series were useful. I enjoyed making them for you, so good luck on the final.